about All right, we can get started with the afternoon session. So we're happy to have Yuji Tachikawa here. He'll be talking about anomalies and topological phases for relativistic quantum field theories. Yuji.
Thank you very much. So I'd like to begin by thanking the organizers for giving me this opportunity to talk. And I also need to thank the local organizers for rearranging my schedule at the last minute, because so I was supposed to talk on the first week originally, but our entire family had stomach and intestine problems due to some virus called rotavirus. My daughter goes to nursery, and as you know, the nursery is kind of like a huge incubation plant for the whatever kind of viruses and germs, and so I'm sorry about that, but luckily I can come in this week, and I'd like to talk about anomalies and topological phases, basically, essentially for relativistic systems. And you have heard already about this topic a lot from Max Metlitsky last week, and I kind of watched the videos online of his lectures for the first 3 of them, which was available, and it turned out that there are lots of overlaps, so I need to restructure my talk, but let's see. So if it felt a bit too repetitive for you, please just interrupt me. And another thing I'd like to say before starting is that I basically gave the same kind of lectures in CERN last year, and some of you just told me that you watched them online. So in that case, that will be a total repeat, and I'm sorry about that, but I'm going to basically repeat it. So to start, as you know, the study of anomalies is an extremely old subject. This Tazi school has also a long history, and there has been a number of good lectures on anomaly in this Tazi lectures. And for example, you can go to archive and just look for Tazi lectures on anomalies, and you find one by Jeffrey Harvey from 2003. I recommend it to all of you, and in it you can find a standard, or I should say old-fashioned way of understanding anomalies in very well explained and in a very detailed way. So you can find almost all about the traditional ways of viewing anomalies in that lectures from 16 years ago, so I'm not going to repeat that. Rather, I'd like to present kind of a new way of viewing at anomalies, inspired by recent advances in the condensed matter physics side of the theoretical physics. So in a word, it's not a word, in a sentence, the essence is captured by the following. So d-dimensional anomaly is captured by a special type, very special type of d plus 1d dimensional topological theory. So this point of view unifies various observations people made about anomalies, both continuous anomalies and discrete anomalies and mixed anomalies. Everything can be captured by this unified point of view, and that's what I'm going to discuss in the lectures I'm going to talk this week. And so this is the essential point, and my slightly more concrete aim is to review various known facts and constructions in HepTH, or even before that, obtained in the 80s, and string theory, from this point of view. I forgot to say in the beginning that I just arrived here yesterday from Japan, and it's about 4 o'clock in the 4 a.m. So I'm pretty sure that I'm going to say something extremely stupid during the lectures. So please stop me and correct me when I say anything totally wrong. So this is the aim, and I have a motto. And I'd like to quote Analects of Confucius. Well, a certain percentage of the audience has East Asian background, right? So I assume that most of you understand. So 211. So which says. Well, I will translate for you. I mean, I don't expect all of you to understand Chinese. So the first letter means warming up, warm up, and this means old, and this is and or then, and this means this letter is to know, and this means new. So in an English sentence, this means that by warming up the old things, you will learn new things. So what I'm going to actually review in the rest of the talk is not really new. Everything is known essentially in the 80s, but I will present them from a point of view, a modern point of view. Does any of you know how this sentence continues in the Analects? Let me just tell you. Well, I mean, if you are Chinese, you should know. So let me explain. This means can, and this can become, or to make. And this is master, indeed. So this means that if you can warm up old things and learn new things from that, then you can become a master in that field. So that's the kind of what I'm trying to do. So the rough contents of my talks are the following. So at the beginning, I will very quickly give you a very general facts about anomalies, generalities, which won't take too much time. And then I'm going to give you a series of examples which shows various types of anomalies, some of which are well known, some of which might be lesser known, and so firstly, I will talk about Dirac quantization of charges from the point of view of the anomalies. And then I will discuss anomaly of the Fermions. Then I will talk about anomalies of the Maxwell fields. Maxwell fields and other antisymmetric tensor fields. And then I will discuss anomalies of of finite groups in 1D, and then I will talk about the same thing in 2D. So those are the examples I prepared in my lecture notes. And then at the end, I would discuss some game you can play with gauging. That was my original plan for my 4 lectures, but as I said, Max Metlitsky already told you about many of the things, so I might need to rethink about exactly what to talk. If after I checked the 4th lecture of Max Metlitsky, after the video is available. So anyway, so do you have any questions at this moment? If not, I'm going to go to the main part of the talk. Is this okay? All right.
I guess I'll just say,
yes,
maybe on behalf of the students, that
yes,
it's not always bad to hear about the same things
good,
from more than one perspective.
Right. Thank you very much. Thank you. Okay. So both Ken and Nati started their lectures by talking about what is a QFT, what are QFTs, and how to think about them. Let me start with a similar question. What does a quantum field theory, say Q, in D dimensions do for us? It's a very general question. One part, so the answer to this question is, it's a vast subject. And at QFT, Q would do for you a lot. But one thing it would do for you is the following. So let's say you have a d-dimensional manifold with 2 boundaries, which is d minus 1 dimensional. What this QFT does for you is that it associates a Hilbert space, right? And for each of the boundary, and then there is an evolution operator which you can write as Z determined by this YD. So this is the evolution operator. So this is a very basic fact about QFT. In particular, when this d-dimensional manifold, YD, if it doesn't have any boundary, if it's closed, then formally you can think of these Hilbert spaces attached to be just one-dimensional complex vector space C. And that's a formality. And you can just think of the this Z, which is known as the partition function. And it's a complex number. This is a complex. So that's what you learn, right? When you learn quantum field theory. You learn that it's very important to compute partition function, and from which you can derive correlation functions by performing functional derivative with respect to the background fields, and from the correlation functions you can compute many other things. So it's very important to compute this partition function, which we learn when you first learn these things, is a complex number. But this is not completely correct when you have an anomaly. So if you learn, when you first learn what an anomaly is, you learn that if the system has an anomaly, if the system has an anomaly, you learn that this partition function ZYD has a phase ambiguity, right? In some sense or other. So when you first learn Tohoku anomalies, I mean triangle anomalies of Fermions, what you learn is that, well, you can compute the partition function under some background gauge field, but if you perform gauge transformation for this background field, this partition function changes the phase. So it doesn't have a unique complex number as the partition function. But an anomalous theory not just have a phase ambiguity. It is very important to remember that it has a controllable phase ambiguity, right? If you don't know how to control it, I mean, that's very much worse than having a quantum anomaly. What's good about quantum anomaly is that you know how it transforms under various gauge transformations. So how do we characterize it? That has been a long-standing question, and there has been many answers to that, some of which were reviewed in the TASI lectures I just mentioned by Jeff Harvey, which involves descent formalisms of anomalies, anomaly polynomials, and so on. And that's very general, yes. But that only applies to continuous gauge symmetries and continuous anomalies associated to that. But there is a more universal way of phrasing what an anomaly is, which applies both to these more traditional continuous anomalies and to another type of more subtle versions of anomalies. So let me rephrase this thing again. I mean, a controllable phase ambiguity. What is that? So this Z is a number, in some sense, a complex number, right, with controllable phase ambiguity. But what is a complex number with a controllable phase ambiguity? Do you know something like that appearing in math? Well, there is a good candidate, which you know. So that is a vector. That is a vector in one-dimensional complex vector space. Without a basis, without canonical basis. Right? What do I mean by that? So let's just forget the physics for a moment, and let's just think about one-dimensional complex vector space V, right? So it's almost like a complex number, but still a bit different, because if you pick an element V, I mean, it's not really a complex number, right? In order to extract a complex number out of this V, what you need to do is to pick a basis basis of V, which I denote by B because it's a basis, then, as you know, V, your favorite vector, divided by basis vector, this is a complex number, right? So I can really write it as an element in C. But that's your choice. If somebody else decided to choose a different basis, that person would consider V divided by B prime, which is a different complex number. And they are different. How are they different? Well, one complex number is related to another complex number you get by this multiplicative factor. So this means that you can model what is happening here about the controllable phase of the ambiguity of the partition function of a quantum field theory by saying that, well, the partition function of an anomalous QFT is not really a number, but it's an element in a one-dimensional vector space. And what we usually think of a partition function is in fact the ratio of that number with respect to a basis vector. So this means that in a very general sense, in order to describe an anomalous QFT Q, you can't say that this partition function for a closed manifold is a complex number. That's not quite correct because it has a phase ambiguity. Instead, you say that this is an element, fixed element of a one-dimensional vector space. So this is a one-dimensional vector space. So this abstract way of saying that it captures all of the controllable phase ambiguities appearing in the anomaly. But it didn't solve the question, right? It just translated the original question into how you would specify this mysterious one-dimensional vector space. So the question is, how should we specify this one-dimensional vector space? To do that, you need a machinery which gives us a vector space for whatever d-dimensional object. Is there a natural thing? Well, if you look at these blackboards, there is almost an answer, right? If you have a, well, we are talking about QFTQ, but this is very general, right? You can change the dimensions. In this blackboard, it says that if QFT is a d-dimensional QFT, it assigns a vector space, which is a Hilbert space, for a d-1 dimensional manifold, right? Here, you need a one-dimensional vector space for YD, d-dimensional manifold. So a natural answer to this question, how you get one-dimensional vector space for d-dimensional manifold, is the following. So what you need to do is to specify a d+1 dimensional theory, let's call it A, such that so this theory A would associate a Hilbert space, right, for d-dimensional theory. And I'd like to demand that this is always one-dimensional, right? Then you can say that this partition function of the original d-dimensional theory is not really a complex number, but is a vector in this Hilbert space of the one-dimensional higher theory. So this way, you see that it will be possible to characterize the anomaly of a d-dimensional theory by using a rather special type of quantum field theory in d+1 dimensions. So what is so special about this d+1 dimensional theory? Well, this part is kind of peculiar for those of you, for people like me who started to study QFT a long time ago. Because when I first learned quantum field theory, the selling point was that it allows you to discuss infinite number of degrees of freedom. So the Hilbert space would be huge. Here, Hilbert space is just one-dimensional. So in some sense, it's extremely simple as far as QFT is concerned. But still, it does the job of describing the structure of the anomaly of QFTs one dimension lower. So let me draw a picture of what is going on. So originally we thought that we have this QFTQ on the manifold YD, but in fact it's better to think that you have a theory A, which is, I use the letter A because it captures the anomaly of this QFTQ. So you have this special theory A in one dimensional higher, and it's better, the anomaly can be usefully characterized by considering this whole setup of having YD on the boundary and with the theory Q and this anomaly theory A in one dimensional higher. So let me just give it a name, WD+1. So in HepTH, you would call this, you are typically interested in this boundary theory. So this is boundary, this is anomalous. This is anomalous QFT. And we didn't have any good name for this, but this is the anomaly theory which characterized the anomaly of that. Quant people would call this theory Q as, say, boundary edge modes. And the theory A would correspond to bulk something called SPT phase. So the good thing about recent developments and recent interactions between HepTH and ConMat is that you can import various concepts and studies developed on the other side to this side, depending on your point of view. So in my case, I was raised in the HepTH side, so I find various discussions in the ConMat side very interesting, and then we are in the process of importing many of the new concepts on this side, and then you need to learn how to translate various words. But once you learn the basics, you start to understand how things get translated. So the point is, again, it's very fruitful to think that the anomalous theory Q lives on the boundary of a special d plus one dimensional theory. So another name you often find in the literature for this bulk SPT phase is an invertible theory. So this is often called invertible QFT. Nati told me yesterday that you don't like the word invertible QFT, and, well, it's useful to know what people call them just to understand the literature. Yeah, so there are names. So these are the generalities, and I'm going to discuss various explicit examples. Do you have any questions at this moment? Yes.
I'm confused by the lack of a canonical basis.
Right.
Because if I take two disjoint copies of this manifold,
Right.
I think the position function should be the product.
That's right.
And then I can use the product structure to choose the one.
That's right.
That's not just giving me a canonical basis.
Right. So
Could you repeat the question, too?
thank you. So the question was, what do I mean by not having a canonical choice of a basis? He said, for example, suppose you have a manifold YD and you consider partition function YD, and suppose you have another manifold and you consider another partition function, then he says that, well, suppose you have a basis here and a basis there, then in the product, I mean, you can consider disjoint union as your space-time, and then you would have canonical basis in the product, right? So that's your point. But the question, that's definitely true, but the problem is that there are many manifolds which is not a disjoint union, right? So you at least need to start with the fact that, I mean, you need to find a basis in this irreducible case. So, right.
In QFT, there's a canonical choice of the basis of the homomorphisms from 1 to 1 because you have a multiplicative structure.
Well, yes, there is a multiplicative structure if you have a disjoint union as your space-time. But if you just have a space-time alone, then the fact, if your QFT is anomalous, it's very difficult to choose a canonical basis. If you can choose a canonical basis, then you can always refer to your partition function with respect to that canonical basis that fixes for you exactly one complex number as the partition function. So then the anomaly goes away. But he made a good point that when we are going to assign these Hilbert spaces, you need to require that for disjoint union, this Hilbert space in which the anomalous partition function takes value in should satisfy this rather mysterious condition that, I mean, if you consider disjoint union, then the Hilbert space needs to be a tensor product, and that's something you need to impose if you want to do this business mathematically precise, and that's indeed true. But the point is that this relation only allows you to choose a canonical basis given canonical bases of the individual ones. Any other questions? Yes.
What are we doing, or what are the conditions on YD such that it has that it is a boundary of, say, a WD plus 1? For example, the real projected plane can't be built from this way.
Well, I mean,
Could you repeat the question?
Thank you. Sorry. So his question was, I mean, can you do this business if you don't know that there is a WD plus 1 for which YD is a boundary? In fact, I'm not using that fact. I mean, I was intentionally imprecise about what I draw on the other side. In order for this formalism to work, YD doesn't have to be a boundary, right? I mean, all you have to have is a one-dimensional higher quantum field theory. This quantum field theory associates a Hilbert space of states for whatever YD, right? It doesn't have to be a boundary. Yeah. Yes?
So on the right-hand board, we say like the QFT associates like a Hilbert space to a submanifold.
Right.
The middle board, we're saying it associates the vector in a space.
Where?
Well, in the middle board, we're saying Z turns YD into a specific vector inside of the space.
That's right.
So,
So thank you for the question. The question was, okay, I think I repeat the question. The question was, what I wrote here and what I wrote there seems not consistent. And yes, it's not consistent. I'm sorry about that. So I started by talking about the general facts about these are for non-anomalous QFTs. Right? So for non-anomalous QFTs, for each d-1 dimensional manifolds, you have Hilbert space of states, right? And you have partition functions which are complex numbers. So that's the standard situation. But in this formulation, anomalous theories are a bit more complicated. For anomalous theories, partition function is not really a number. It's a vector in one-dimensional vector space. So that's the answer. And these things become more complicated if you want to be completely mathematically precise for anomalous QFTs. Any other questions? Yes?
what are the conditions for the CA to exist?
So the question was, when can a anomaly of a QFT can be captured by one-dimensional higher theory? I don't know. That's a very good question. Many things which are called anomalies in HEP-TH literature have been by now translated into the language of this one-dimensional higher theory, but there are a few which haven't been translated this way. I mean, first of all, I don't know I don't know the situation about conformal anomalies. Yeah, is conformal anomalies captured by D+1 dimensional theory? I doubt it. I'm not sure about that. And there's also a very subtle type of anomalies in supersymmetric theories, like shortening anomalies, right? Found by Nati and collaborators. I don't know whether it's captured by a theory in one higher dimension. So it will be a nice thing to think about. So you can go over literature and find various other types of anomalies and what would be the interpretation in terms of one-dimensional higher QFT. Yeah. So a lot of various diverse type of anomalies can be captured in these formalisms, as I'm going to demonstrate by examples. But yeah, I don't know whether it covers all. Thank you. Any other questions? Yes?
So usually we think of a QFT as a function from cobordisms to Hilbert space. So you're saying for anomalous theory this can't work and you need is it like a projective?
Yeah, so let me repeat the question. So the question was, so he asked me, usually on the very mathematical side of community, people think of QFT as a functor associating, Hilbert space to d-dimensional one manifold, d-1 dimensional manifold, and morphisms for d-dimensional manifold. But that only applies to non-anomalous QFTs, yes. For anomalous QFTs, that needs to be generalized. Yeah. In fact, this point has been noticed by mathematicians long time ago in the early 90s. If you look up very careful literature from those days, originally Atiyah and others came up with the idea of using category to describe QFT, and then Witten came up with this idea of Jones polynomials and how to associate topological quantum field theory for Chern-Simons theories. And then mathematicians try to combine the both ideas by idea of Atiyah and idea of Witten. And immediately they ran into a lot of, subtle mathematical problems because of the fact that the Chern-Simons theory has gravitational anomalies. And there are lots of confusing literatures on this point, right? But the point is that you need to attach space-time with one-dimensional higher, and you need to consider theory, some very special theory on top of it. Any questions? All right. So let me start discussing examples. And many examples I'm going to discuss, in fact, have been discussed by previous lecturers, but let me do that anyway. So example 1. So it's a Dirac quantization. Maybe I should not cite the original works, but I couldn't resist. So this work is originally done by Dirac, in 1931. So it's almost a century old. So this is Dirac quantization. So, but I will present in a way different from the original paper by Dirac, right? But let's consider 0 plus 1D QFT, which everyone knows is just another name of quantum mechanics, and coupled to background U1 field. So I watched the videos and I noticed that Greg discussed the case of particle moving on S1, which is one example. And Nati just discussed the case of Dirac fermion in quantum mechanics coupled to U1. So those are two examples. I would discuss more, in some sense, extremely trivial example. So let's say you have S1 as a space-time for the quantum mechanics, and you have background U1 gauge field A, right? And so let's say the integral of this A dx, I'm somehow parameterizing this circle as x, and you integrate that, right? And you consider exponential of I phi, which is a group element, which is in the U1, right? So Greg and Nati discussed how such a system arises in two specific cases of a particle on S1 and the case of a Dirac fermion. But let's forget about the details, and let's just say that the partition function ZQ S1 with this group element G turned out to be exponential of I times Q times this integral of A dx, which is this group element G to the power Q, right? So this is well defined complex number if Q is an integer. So this point was emphasized again and again, and I'm saying that again, but not well defined, right? Not well defined if not. So this can be thought of as a phase ambiguity, and this is an anomaly. So how do we characterize Sorry, it didn't go all the way up. So how do we control the anomaly? How do we control the phase rotation? So one way can be as follows. So I'm just repeating the equation I wrote there. G is exponential y phi, and this means that phi going to phi plus 2 pi, that shouldn't change G, right? But when Q is some general number, IQ phi changes under this transformation, and this becomes IQ phi plus 2 pi, which is an original IQ phi, but with some additional phase factor, I 2 pi q. So this way, the phase ambiguity is controlled, under control. So it's not as bad as losing the predictability completely. So that's one way to control the anomaly. And another way was also mentioned by Nati, which is to attach a two-dimensional manifold. So let's pick. So what you do is to attach some two-dimensional manifold. Say, I'm using the letter W, so let me use W. And let's pick some theta over 2 pi, which is equal to Q mod 1. So you need to choose something. And then you consider the bulk theory, which is just classical, has this action, F over 2 pi. So this F is the gauge field strength, as everyone knows. So in this setup, I had this term as before on the boundary, and you now have a bulk and the bulk provides this term I theta F over 2 pi W. And as already mentioned by Nati, the combination has a definite value, which is good. But the problem is, the fact that the original thing had a controllable phase ambiguity is translated to the fact that the value depends on how you extend the manifold and how you extend this gauge field to F. So you consider different extension. And the point is that this value and this value, they are both the same. Both definitely defined, but they are different. They are different. How are they different? So the ratio of this thing and that thing is exponential of I theta integrated over w minus w prime of f2 pi, where you can visualize w minus w prime as, you have this original manifold w, and that contributes this integral, but you want to subtract that, right? So a useful way to consider the negative of that exponential is to consider the orientation reversal of w prime. So I'm just calling it minus w prime. And you consider the entire closed space-time, and you evaluate this bulk action there. Yes?
I think this is obvious, but f on w prime is different, but you're just calling the extension on that side f as well?
That's right. The question was, I need to repeat the question, but I wasn't perfectly precise when I use this symbol f for the f extended on this side, because I took the orientation reversal. Yeah, but yeah. Is it the sound of a rainstorm? Okay. So the point is that if you integrate f over 2 pi on a closed manifold, and it's an integer, right? So it's an integer n. But for general theta, this is not, of course, 1. So this means that the definite values you obtain by extending the gauge field and the space-time to one higher dimensions depends on how you actually extend. So these are two ways of understanding anomalies. One is this way of controlling the anomalies. Another is to ascribe them to a different choice of the extension, right? So in a sense, what I did was to derive the electric charge quantization, assuming that you already know that the gauge field is described by a U1 gauge field, which is geometric and has this definite quantization of the magnetic charge. So once you assume that magnetic charge is quantized this way, in order for the partition function of 0 plus 1 dimensional quantum mechanics not to depend on the extension, you need to have the charge, electric charge, to be integer. So that's one way to understand Dirac quantization. So Dirac quantization is a way to say that the electric charge of a world line is non-anomalous in the presence of non-trivial electromagnetic field. So that's the example 1. Do you have any more questions about example 1? I think this has been discussed so many times in this TASI school, so I think everyone understands that. Good. So the next example would take more time, and that's the example 2. So I would have 50 more minutes, right? I guess.
Yeah, more like 20.
20, okay. So I'm going to talk about massless fermions. So massless fermions famously have anomalies. It's the first system where people notice the anomalies, and it's in some sense the first system where people understood that the anomalies is characterized by having one-dimensional higher spacetime. And again, it's discussed already by Max Metlitsky and also by Tom DeGrand in the lattice setup. So let me just recap what you learned from them. So it can be any dimensions, but for the sake of definiteness, let's say you have 4D system and 5D bulk. And let's consider Dirac, 5D Dirac fermion with varying mass, right? So you can see the top, but I think it's not too complicated to draw the graph on top of this. So let's say that the mass term of the 5D Dirac fermion goes something like this. From 0, plus m, and minus m, right? And I'm not going to repeat how you derive the existence of the zero modes, because Tom Degrand had a nice discussion of that. But what you can learn from solving the equation, Dirac equation in 5D, is that you have a zero mode concentrated on this transition region of the mass parameter, and it has a definite chirality. So the chirality depends on whether the mass goes this way or mass goes the other way, right? If you say this corresponds to the positive chirality, this corresponds to the negative chirality. So the entire 5D system is non-anomalous. Therefore, this means that if you embed anomalous chiral fermion system in 4D as arising from this position-dependent mass of a 5D fermion, then the entire system has a definite partition function. So you can use this 5-dimensional massive fermion system as the one-dimensional higher thing that controls the anomaly of the 4D chiral fermion. So it appeared in many places. It appeared originally in Cal and Harvey in Western Europe. But on the same year, Shatashvili and Fadeev had basically the same idea in Russian paper. So again, ascribing who found the concepts first is a difficult business, but it's long known. So in this sense, in order to understand the anomaly of a 4D fermion, you can just think about 5D fermion, right? But that's a bit too much in some sense, because 5D fermion system still has infinitely many degrees of freedom. It's a quantum field theory with local excitations, right? But that's in some sense a bit overkill. As I said in the generalities, when I discussed generalities, you only have to use a very simple QFT in one-dimensional higher, for which there is only one state in the Hilbert space. So you can just throw away lots of physical info about the one-dimensional higher theory if the only thing you want to do is to characterize the anomaly of four-dimensional theory. So how would you do that? Well, first of all, this is a bit different from the picture I draw here, right? here I extended the spacetime only on this side. But in this picture, in order to describe the anomaly on the boundary over 4D, I needed to extend the spacetime on both this direction and that direction, right? So that's a bit different. So I first do a trick of flipping this side on the other side, which you can formally do, right? So you have you just flip this side on the other side, but this makes this anomaly theory to have the partition function of this form, 5D fermion with positive mass, but because you flipped this thing on this side, well, you have to divide it by 5D fermion with negative mass. So the anomaly theory formally has a partition function which is given by the ratio of the 5D fermion with positive mass and negative mass. And this still has lots of degrees of freedom, but we just want to characterize the anomaly. So let's just take the limit where the absolute value of the mass becomes infinite, right? So that propagating modes become extremely massive and goes away. So this is the partition function of the one-dimensional higher anomaly theory, which characterizes the anomaly of the 4D fermion. So this thing is known as exponential of 2 pi I eta, where this is the eta invariant. I'm sorry to say that I'm using a different convention than the convention used by Nati. So there's a factor of 2 difference. So I should say that in the Atiyah-Patodi-Zinga paper, where this thing was originally introduced, they used both eta invariant and the Xi invariant, and this is in fact a Xi invariant, unfortunately. Right, and right. So, but the important message I want to tell you is that when I first heard of eta invariant appearing in this business, I was very scared. That looked very complicated and scary. But in fact, it's not. I mean, very scary. And it's in fact very computable. In any case, it's just the ratio of partition function, the free theory. So it's nothing to be worried about. This is something you can actually work on, and which is something you can compute. So very formally, eta invariant is computed by taking the limit, and you just compute the ratio, right? And because eta is the log of the partition function, this just becomes a sum over all Dirac eigenvalues of Dirac operator. And because I pulled out a factor of 2 pi, I need to divide by 2 pi. And you and something like this. And because I'm a physicist, I'm going to use an extremely bad way of, non-guaranteed way of computation by exchanging the order, right? And taking the mass going to infinite limit. And if you do that very formally, you get that this is given by 1/2 the sine of the eigenvalue E. And in my convention, sine Sine of 0 is +1. And sine of positive thing is +1, and sine of negative thing is -1. But of course, this needs to be regularized. So I would put double quote. So to compute the eta invariant, you need to use some regularizations. And if you look up math papers thinking that you want to learn how to compute the eta invariant, invariably they use zeta function regularizations to compute. But you don't have to use zeta function regularizations, because in any case this is just the ratio of the partition functions of a Fermion system, right? And we know that whatever regularization scheme you use, you get the same answer. So in fact, you don't have to use the zeta function regularization. You just have to use your favorite regularizations, and as long as it's a reasonable one, then you get the correct answer. So, right. So let's do some exercise. Right. Let's do some exercise which is related to Natty's example. Yeah, I still have 10 minutes or something. So let's consider U1 charged Dirac Fermion on S1, right? S1. And let's say the holonomy is phi, so G is exponential I phi. Right. Remember that Natty used this to discuss an anomaly of 0 plus 1 dimensional system. But I'm using this as to characterize the anomaly of 0 plus 0 dimensional system, because I'm using this as a bulk theory with mass. But anyway, here Dirac operator is just, partial x plus phi, right? So the eigenvalues are just n plus phi over 2 pi in some units, right? And of course you can use zeta function regularizations, but I prefer not to. So let's use, exponential. So this is E. This is E. The standard regularization you use is this exponential regularization, right? To regularize. And then take the limit where the regularization goes away. So eta is limit of goes to 0, 1/2, and sine of n plus phi over 2 pi over n, and exponential of minus t n plus phi over 2 pi. This is extremely simple to compute because this is just a sum of exponentials, right? It's a geometric series for both positive and negative n. You need to be careful about where this turns positive and negative, but this is extremely simple to compute. This becomes 1/2 minus phi over 2 pi. So this means that exponential of 2 pi I phi is, in fact, because of this 1/2, you have minus, and then you exponential minus I phi. So this is the end result. Again, there are a few different conventions, unfortunately, for the eta invariant, and I'm sorry about that. But the important thing, yes, pardon? Thank you. Natty corrected me the alphabet. Yeah, I repeated the comment. Thank you. So the important thing is this entire exponentiated versions of the exponential, and nobody has any different convention for that. So this is the final answer. So this just meant that the bulk theory, after you integrated out the massive fermion, behaves, this behaves as exponential of I integral of A, IA. So this explains, from path integral point of view, the shift in the level K by 1 when the mass between the positive mass and the negative mass. So, right. So I'm going to give you another example of computing eta invariant in a specific manifold tomorrow, but I'd like to end today's discussion by mentioning a more general case. This type of explicit computations of eta invariant is only possible when you know the entire Dirac spectrum, which is not always the case. It is often the case in a lot of cases, because you often are interested in a very symmetric type of space-time, but very generally it is not. So in that case, how do you compute the eta invariant? So let me just say to you. So I should very quickly remind you that originally we'd like to discuss the anomaly of a fermion on d-dimensional manifold, and you discuss the anomaly by considering one-dimensional higher space-time, and you consider ratio of Z fermion and Z fermion, and mass very positive and mass very negative. So you consider this, right? And just as before, this depends on how you extend. Suppose you have various holes. So again, you have Z fermion here and there, and you want to discuss the ratio. The ratio is this is Z fermion M very, very large over Z fermion M very, very small, evaluated on the combined manifold, obtained by attaching this WD plus 1, and this part is WD plus 1 prime. So in order to characterize the anomaly of a d-dimensional fermion, you would like to compute this ratio of the fermion, massive fermions, on closed d plus 1 dimensional spacetime. And as I said, that's just a definition of the eta invariant. But how do you compute that? Maybe I should go here. But then how do you compute? So now we have this combined spacetime of W and W prime with a minus sign, but this is a closed manifold. And suppose you can further extend it to D plus 2 dimensions. So let's call this U, D plus 2. Then there's a very nice theorem called Atiyah-Patodi-Zinger theorem, which says that the eta invariant of the boundary is equal to the number of zero modes of Dirac operator on U plus the integral over U D plus 2 of this standard anomaly combination. So this is the APS theorem. Yeah, I know I need to wrap up. So I have a few comments about this APS index theorem. So when you learned anomalies in your standard QFT textbook in some advanced chapter, you have definitely seen the standard Atiyah-Zinger index theorem, right? That looked very similar to this. But the more standard Atiyah-Zinger index theorem is about when partial U, which is W, which is empty, right? In that case, you don't have this left-hand side contribution, which is the eta. So this becomes a theorem giving you, the index of the Dirac fermion in terms of this curvature integral, which is very useful. But here, we are interested in just this exponentiated combination of exponential 2 pi I eta, right? So for the usual application of the APS theorem, you are mostly concerned about computing this index, which is an integer, right? But for the computation of this eta invariant mod 1, if you raise it to exponential of 2 pi I, the index part fortunately goes away. The problem is that usually you don't have any control of the index on this open space. But it's good that it is integer, and it goes away. So if you raise it, you just get eta invariant exponentiated. It's just exponentiated curvature integral. U trace f2 pi. So this is one way to compute the eta invariant for very general situations. So if you happen to know a D plus 2-dimensional space U for which the boundary is the W you are interested, then all you have to do is to just compute this curvature integral, so which might seem more tractable to you because it's just a standard integral of differential forms. Yes?
The APS theorem tells you that there is no anomaly in odd-dimensional space-time because the curvature A group genus is only defined for even dimensions.
So the question was, does this mean that there's no anomaly in the odd dimensions because this thing only has even dimension terms and this vanishes? That's a very good point. But so the answer is the following. This means that if you consider odd dimensional D, for which D plus 1 is even, for which D plus 2 is odd again, this term is just 0, so this term is just 1. But that assumes that this D plus 1 2-dimensional, you can find such a U for which your W is a boundary, but that's not always the case. So this tells you that the anomaly of an odd dimensional fermion can only come from a D plus 1-dimensional space for which you cannot find such a U. So thank you for pointing that out. And but yeah, right. So I'm going to really stop by applying this case, this theorem, for this very simple case, right? For a very simple case. So how do you apply that? How do you apply that? So this S1 is W, right? And you definitely know a good manifold for which S1 is a boundary, right? This is just a disk. So this is U. So you apply that formula, and you immediately conclude that exponential 2 pi I eta is exponential of just f of 2 pi right, over U2, right? And this gives you, and you can easily partially integrate, and this gives you exponential I phi, right? And you need to accuse me, or I mean, there's some sign convention which was wrong, but you need to be angry about me, because here I wrote, no, I mean, this part is okay, but what is this minus sign, right? You should worry about it, and I didn't get the minus sign. So the point was that I implicitly chose, when I computed this eta invariant, the periodic boundary condition for the fermion as the 0 point of the U1 phase. But that doesn't extend into the disk. So when you learn string theory, you are everyone gets confused about the NS spin structure and the R spin structure and how they transform between cylindrical coordinate and the disk coordinate. And that's what's happened here. And so this exercise I just did in front of you shows that you need to be careful about whether all of the data you have on your manifold correctly extends to the on the boundary, it extends to the bulk. And the good thing about the eta invariant is that it's computable, but it's very sensitive to very subtle data like spin structure and etc. And I'm going to discuss a few more examples tomorrow. So thank you very much.
We had a number of questions already. Any more? Okay, well, if not, I have good news for you. So the band I'm in was playing a house party last night. You may be wondering why that's good news. And the reason is they had all these leftover cookies. I thought the Tassie students might like those, and maybe the lecturers too.
Yes.
So I'll put them out with the coffee. So let's thank Yuji again.